In a previous lesson with Heather, we calculated the right Riemann sum for four 400 and n rectangles for f of x equals 5 minus 1/2 x squared on the interval from 0 to 2. So if we look at all of our work that we did before for n rectangles, we used all this sigma notation and we ended up at the end, after we simplified, with a function in terms of n. So now if we want to find the exact area and not just an estimate, we want to take the limit as n goes to infinity of this function. So we have 10 minus 2n plus 1 times 2n plus 1 divided by 3n squared. Now to take this limit, first we notice that if we just try to plug in, we get infinity over infinity for this fraction. So there's a couple ways we could go about it. Maybe we're thinking L'Hopital would make good sense. But actually there's an even faster way to calculate this limit. If we look at the top of this fraction, if we were to multiply together the first highest powered term in every piece, we would get 4n squared. And in fact, if we were to FOIL everything out, we would get 4n squared plus 4n plus 2n plus 2. But we don't really need to do that. We only need the highest term. So we can get rid of all the rest of this. And then we can remember that we actually had a theorem way back when we were doing limits that said if you're taking a limit to infinity or negative infinity of a function that's a rational function with the same power on the top and the bottom, maybe something like this, then all we have to do is take the coefficients in front of the highest power of x. So here we would get 5 over negative 1, which would be negative 5. And that's the answer to the limit. Note that you have to be going to plus or minus infinity, and you have to have the same power. So this limit becomes 10, because it doesn't have any n's in it, minus 4 over 3. And that's the exact value of the area that we were trying to find. If we simplify this a little bit, this is 8 2/3. Now let's try this one more time. On a previous video with Heather, we also used this same function and calculated it with left Riemann sums for 4 400 and n. Alright, so that when we evaluated this limit, we ended up with this equation right here. So from here, let's go ahead and take the limit of this equation as n goes to infinity, and we're going to need to distribute this 2 over n to every term. So we're going to be taking the limit as n goes to infinity of 10n over n minus 4n times n plus 1 times 2n plus 1 divided by 6n cubed plus 8 times n plus 1 divided by 2n cubed minus 4n divided by n cubed. Alright, so now we want to take this limit. Since there's a lot of kind of complicated terms, let's go ahead and write it out one more time using the limits of highest powers rule. So this is the limit as n goes to infinity of the highest power, and the first term is just itself. In fact, we can just cancel those n's and call this 10, minus the highest power of 4n times n plus 1 times 2n plus 1. We want to multiply 4n times 2n, and that gives us 8n cubed, divided by the 6n cubed we have on the bottom, plus here we have 8n times n, so that's 8n squared, over 2n cubed, minus we have 4n over n cubed. So now what? Well, the limit as n goes to infinity of 10 is just 10. The limit as n goes to infinity of 8n cubed over 6n cubed, well, the n cubes cancel, and that is 8 over 6, because they're the same power of n. Now for these last two terms, the power of n on the bottom is bigger, so notice if we simplify, we still have an n left in the bottom. And if there's a constant on top and an infinity in the bottom, we know that that goes to 0. So this limit ends up being 10 minus 8 over 6, which is 8 2/3. So that's the area under f of x equals 5 minus 1/2 x squared from 0 to 2. Notice that we got the same answer for the exact final area, whether we used the right Riemann sums or we used the left Riemann sums. This should make sense, right? Because we're finding an area. It should have one number as the answer no matter how we find it. And this leads us to believe that if we want to find the exact area, we can actually take our rectangles however we want and we'll still get the same answer. To actually formalize this, first we need to define what we call a generalized Riemann sum. This means exactly what I just said. We can make our rectangles however we want. So we can make them with all different widths. We can choose what value we want to use to plug in to find the height in all different ways on every rectangle. And what we want to claim is, if we have a generalized Riemann sum like this, there is a class of functions where no matter how we find the area, no matter how we take the rectangles, we always get the same answer, and we're going to call those kinds of functions integrable.